So good afternoon, everyone. Hello, thank you for coming. I am Patricia from Erudite Reliability Services, and on behalf of the team, I would like to welcome each and every one of you, as well as thank you for joining us today. So this is an hour and a half webinar for Introduction to Condition and Remaining Life Assessment of Power Utility as Assets. Just a gentle reminder to keep your microphones on mute during presentations unless you have questions. You can always raise your hand or chat them on the chat section here on Zoom. We will also have a Q&A session afterwards the presentation in case we've missed any of your questions. All right. So yeah. So without further ado, I would like to introduce to you our speaker for today. So he is a registered professional engineer specializing in electrical failure investigation. He has over 16 years of experience and has conducted 200 plus root cause investigations across the globe. His expertise also extends to renewable energy projects, including large-scale solar plants and offshore wind parks. In 2023, he started Volta Engineering and Inspection, offering his forensic engineering services to various stakeholders in the energy sector. Okay, so everyone, uh, join me in welcoming our speaker for today, Mr. Rafiq Khan. Mr. Rafiq?
Thank you, Patricia. Hello, everyone. I think I don't need to really introduce myself. Patricia did a very nice introduction of myself. So today we are possibly going to touch a few aspects of condition and remaining life assessment, mainly for power utilities. I will share with you my screen. Please let me know if you can see it. Yes. Okay. So I assume that most of you are either people from electrical background or some areas related to energy, and you do have a lot of assets under your organization. So when you have assets, you always want to know how long you can run them for and how much more can you use them for benefiting your organization. So what I will start off is just a brief introduction about my company. So I started a small company doing failure investigations. We are based in Malaysia, but we also operate around the APAC region. Our focus area is in power failure investigations. Power failure investigations meaning we do electrical investigations for various type of customers, stakeholders, mainly for court cases, for example, insurance, warranty claims, continuous improvement of systems, accidents, loss of life, what have you. I also carry out expert witness roles, technical consultation, technical training, and inspection. So these are areas that are mostly related to power failure investigations or electrical failure investigations. And what comes out of the knowledge of the experience gained over the years. What I am also happy to share is that this term that I call the Volta Forensic Edge. So we are able to provide a comprehensive approach to failure investigations. Although I'm an electrical engineer by learning, but failure investigations involve various sciences, materials. You need to know also a bit about the environment and other aspects of operation. And so we are able to incorporate a lot of these areas into a failure investigation to make it comprehensive, mainly by our network of experts and also testing laboratories, which we have known over the years. So we connect everyone, make a team, and try to attack the problem of failure investigations together. So the next topic is the next slide covers the topics that we will cover today. So for your information, this is just an introduction of condition and remaining life assessment. It doesn't cover all the aspects, but it is meant to be an introduction, a first step for you to understanding what is condition and remaining life assessment. So we will cover the introduction, we will cover remaining life, we will cover a bit on isolation degradation, what is condition assessment and what is condition remaining life assessment, some concepts of maintenance, and a bit on the replacement decision making, when to replace an asset, and future trends and technologies. So I hope you can bear with me, but if you have any questions in between, which are burning questions that you think are important to address during the presentation, please feel free to stop me and we can go from there. We have about 1.5 hours. So I will cover topic one first, introduction. What is you are seeing on the left, the circle is called the cradle or to grave cycle of an asset. So it always starts with specifying what you need for this application, then designing to the need that it is meant to be used for. Then we go into manufacturing, installation, commissioning, operations, maintenance, and decommissioning of an asset. The one that you see with the smiley faces there, those are the areas where we will be looking at in terms of condition and remaining life assessment. So starting from when it is commissioned up to the end before decommissioning, this is where condition and remaining life assessment plays a role. On the right is a typical bathtub curve. So bathtub curves are just curves of when failures happen in the lifetime of an asset. The topmost one is what you typically see, which is the bathtub curve again. You look at it and it does appear like a container or tub. And early on, it starts to fail a lot. After a certain period of time, it stabilizes. Not so many failures happen. And towards the end of its life, you see increasing failure rates. So this is just in another word, there is also a term called the Y-bull analysis, where we look at when the asset is failing and what stage of life and the related problems that could have happened. The second graph, the red one, it shows the early infant or mortality time. This is normally typically associated to installation errors when people install an asset, non-compatibility between asset and use, sometimes also wrong specification for the intended application, where you have possible of high current need and you have a very um, small conductor. Then you have issues with heating, overheating, and failures. The next one, which is in yellow here, is wear out failures. As the asset wears out or age, then your failures start to increase again. So early infant mortality failure, they happen early on, and after some time, you don't see it anymore. So you can actually, for a certain manufacturing design, you can already look at the rates of failure and determine if it's something related to installation, if it's something related to non-compatibility. So you will see a trend there. Wear out, it develops over time. The more you use it, it begins to wear out, it begins to age, and then you have more and more failures developing at the end of an asset's useful life. So here's an example of a lifetime estimation. So a lifetime estimation is normally based on design. So what is the equipment designed for? And they do also have some laboratory testing, artificial aging, for instance, applying some form of stresses to the equipment, and then they determine. This is an approximate only. It's a statistical type of remaining life. So it doesn't say that you have an asset that is in use today, 40 years later, that definitely is going out of service or is going to fail. But this is based on, yeah, like I mentioned, design, laboratory testing, and sometimes also involving nowadays a lot of simulation work. What can happen to an asset when it is being in use? So in real life, it is a non-ideal condition, not a simulation, not a laboratory testing where you control the environment, but non-ideal conditions arise. And these non-ideal conditions, they in turn have an impact in the lifetime. Sometimes it reduces the remaining life, sometimes it extends the remaining life. Some aspects to consider are condition when it is assessed, stress history, loading, for example, if you have a transformer that is being loaded heavily, it starts to age fast. So you have a reduced lifetime. Mainly loading and temperature, they go together. For example, also, if you have a transformer that is half loaded, not fully loaded, but only 50% of the design, specified design you load it to, then you have reduced temperature and possibly you can extend the remaining life. So this is a statistical number, of course, but you can improve or make it worse with your actual operation. You can look at failure history, previous damages. If you see a tendency for certain things to go wrong fast, then those statistical graph starts to move to the left, and you look at possible early retirement. Maintenance history, known design weaknesses. Those are things that by trend, you look at certain manufacturers, for example, they come out with a new design, and then this design is not really tested out fully in field yet. But then you start looking at it, and you know that there are certain design weaknesses, and then they need to do improvement. So this is an area of interest nowadays with more reduced cost or cost efficiency type of production. So you look at this as well. Not always when you put an equipment into a system, for example, a cable, a switchgear or transformer, when you put it into a circuit, you know that it will remain serving the same load. Nowadays, we have a problem also with load increasing. On the load side, you are connecting more and more devices, more and more equipment. Electric vehicles are being charged. And when you have this kind of situation developing, you will have an expected lifetime that is reduced. So things can become different over the years. So we tend to have to look at them as we progress. The second topic is fundamentals of remaining life. If anyone has questions, just please interrupt me or put a message in the chat. The concept of remaining life. I like to use this term, remaining useful life, because actual life of equipment can go beyond a certain age, depending on the use. But we want to have a minimum acceptance service level. When we can already retire the equipment is based on how much risk we are carrying. So probability of a failure happening is one way of determining the remaining life of an asset, and also the corresponding risk. So as we progress, for example, in distribution systems or even in plants, we try not to have more failures happening, because failures result in interruption, and interruption costs money to the operation. So there is a minimum acceptable limit where we want to operate. The more failures happen, the more losses. So we want to play a bit higher above than the minimum level. And so the end of remaining useful life is often determined as the limit where we can take this risk. Uh, any forecast and uncertainties. So when we look at past performance, what is happening, like I mentioned just now, we can also have issues with load increase. So it cannot be used for all time. The first time you do a forecast, it cannot be used for all time. There needs to be a timely or continuous approach into understanding what is happening in your assets. It's also based on assumptions of future stress, load, temperature. When you have more load connecting, uh, when you, sorry, when someone said something, okay, Yeah, so when you have more load connecting to an equipment, you might need to adjust these assumptions. So the best we can do is to predict future failure versus probability of failure. Sorry, probability of future failure. But there is a part of it which also remains important, that we know more. The more information is given to us, the more accurate the forecast becomes. Okay. Like I mentioned also earlier, conditions can change, like situations when you have increased load over time, but there are also moments when you have events. Load increase over time, it comes quite gradually. You don't have a spike in a system that suddenly goes very high or very low in the insulation property. So for example, the graph that I show on the left here, the one that is related to aging is the blue line, the gradual line. But degradation in the insulation can happen quite abruptly. It can be also a stepwise drop. And things like transient over voltage, when you have lightnings or switching, those can result in this kind of pattern. External mechanical impacts, let's say when they do some form of handling during installation, and you have displacement of parts inside a component, then you can also have a stepwise decrease in the insulation breakdown strength. Sudden changes in the insulation can also be a result of things like a flood that suddenly comes over a night, and then you have moisture ingress in the switch gear. Takes some time to dissipate out moisture, but then you see a stepwise degradation or reduction in breakdown voltage. Yeah, we mentioned also material degradation, environmental condition, maintenance practices. Maintenance practices, sometimes they say if it's not if it's not faulty or damaged, don't fix it, right? This is also quite true when we do failure investigations. A lot of failures happen after fixing or maintenance practice. So it's not to say that you don't have to do maintenance, but you need to do it correctly, because otherwise you have a situation that developed which was not previously present. Maintenance can be a problem as well. So how to improve the patterns that we see? If it's aging, maintenance can offer some help to a certain extent. Of course, you cannot maintain everything to run forever, but it does help. If you have wearing of parts, maybe some repair can be done. If it's mechanical, we can actually do some form of repairs. If it's an event which results in a very large degradation pattern, then often we try to replace, because we don't know where this is heading to. It's not something that is gradual. You cannot trend it. So that's something that we need to replace. There are also moments when things become obsolete, or things become no longer feasible to look for spare parts. Then you might need to upgrade. Also, sometimes things like system requirements, they also need some upgrade. Then we go into upgrading practices. Topic 3 is insulation degradation. So this is something I learned from my former organization. They do a lot of failure investigations as well, and this is thermal, electrical, mechanical, and ambient. In their terms are ambient, but I'm putting here as other modes. Thermal impact is something that is quite prevalent in power systems equipment. So heat will lead to decay of insulation properties, and then you have a design lifetime that is reduced. Something that can be put as an example is, let's say, for an XLPE power cable, XLPE insulated power cable. During the manufacturing processes, these cables are degassed where methane is being pulled out of the XLPE, cross-linked polyethylene. You don't want to have gas bubbles forming inside these cables. So during manufacturing, they put in these cables into ovens, which are about 70 degrees C. So you know that during manufacturing, cables are put to about 70 degrees C. After manufacturing, they come to about ambient temperature, and then they are installed in service, put in service. But sometimes there are also issues related to termination issues or which are bad contacts, and these points have temperature rise. You have also extra loading that can result in temperature rise of the core. And so what happens is that we normally say that 90 degrees is where SRP insulation starts to have its limits. There is a temperature slightly above here, which is about 100, 110 to 112 degrees C, which is called the glass transition temperature. And often when you go above 90 degrees C, the degradation starts to become fast. So they say also in some papers that if you go by 10 degrees, you halve the life of this insulation. So thermal degradation is a real problem. You also experience it in transformers. In the photo here on the top right part, top center part, we are looking at the insulation paper insulation of transformers. And when you have high thermal aging happening, you will also have degradation of mainly the primary insulation material in transformers, which is paper, but also because there are spaces in between this paper, which is called high density press board. These are also aging at the same time, but the main function of these press boards are to mechanically put everything in place, space between the windings. And when you have aging of this, it starts to sag, it starts to collapse. This is a problem where you have the conductors, the windings start to come closer to each other. So transformers also face thermal aging. Electrical degradation, it can come from high electric fields, that are discharged over insulator. The one that you can see at the bottom here, you can see that this cable has whitish deposits. There are greenish also corrosion materials. It's quite common to see this in electric installations. And what happened here is that you have a high electric field, and high electric field results in corona or ionization of the air. Corona in turn, corona produces nitrogen, a lot of nitrogen. Where you have moisture, it comes in contact with moisture and makes nitric acid. So nitric acid is the one that is creating all this problem that is visible, but the initial stage is electrical field. The visible problem is not electrical field, but a result of electrical field. Mechanical degradation, of course, if you have motors, you have the bushings where moving parts wear out. These are quite common. You can also have wearing due to vibration. Static field cyclic mechanical load. Not going to touch too much into that, but it's quite frequently seen, this kind of insulation degradation mechanism. Solar radiation, for instance, in cables which are meant for underground installation, these are not cables that you want to put outside in the sun. So you have PVC, HDPE, or what other materials which are exposed to the sun, they begin to crack. Solutions for it sometimes are also graphite coatings, which cover these primary plastic parts. Graphite is a bit more inert and doesn't react with the solar radiation so fast, at least not so fast, and it gives a bit of a lifetime. Chemical degradation, it can come from acid or chemical spills. It can be contaminated environment, moisture ingress. In tropical countries like ours and Philippines, we see a lot of issues with moisture ingress, where substations are not managing the moisture problem. You see corrosion, and corrosion also results in some form of reduced breakdown voltage in the air insulated compartments. Reduced breakdown voltage in vacuum or insulating gases. Sometimes we have leakages, which is resulting in which results in release of gas or vacuum pressure. Then you have also contamination and reduced breakdown voltage. So these are all things that affect aging. It can become faster because of different mechanisms. Topic 4, we are going to cover a bit about condition assessment. So this is again only a fundamental part of it, but I think it will give you some idea for your own use in the future. So by definition, condition means condition, the situation, the condition assessment. So it's a process of evaluating the physical state and performance and overall health of an asset system. So it's a lot of words, but what we need to know here is what is the current state of the asset. What is it, the situation of the asset, the age of the asset, the physical condition of the asset, uh, whether or not it's delivering certain performance that we need, and is it operating as intended? Is it deviating from the intention of how it's supposed to operate? Are there signs of deterioration, damage, or wear? And what are the risks that we have with the current condition? If it goes on for, let's say, 5 years, can it survive? Will it fail? Will there be issues related to loss of life or breakdowns? What are the risks? What are the actions needed to maintain or improve the asset condition? So these are questions that we ask during condition assessment. So what does it tell us? Condition assessment, again, because of the questions that we ask, we are able to answer this as well. Type and degree of degradation or defect. So we look at failure history, we do visual inspections, some form of testing or detection methods, and also destructive testing. So destructive tests sometimes involve failure investigations, where we dismantle parts, look at the insides, identify root causes. Those are possible ways of doing this kind of assessment. Criteria for urgency. So if you have 100 switch gears in your asset, you can also look at the failure probability, and you can look at what are the causes, and the consequence. So whether or not directly it's going to affect your operation, or indirect, is it going to be a performance issue and not just a breakdown? So those are things that you can start to prioritize. So if, let's say, an asset has a very high urgency, we want to replace or repair it quickly. So these are things that give us some power to decide. Plan action. When you have criteria of urgency, you can plan. So if you need to do it for short term, you can do a short term repair, run it for a certain time until there are replacement parts, and we can replace it. We can do also a detailed diagnosis to see if, let's say, we think this insulation is going to function for a certain period of time, but we can use it at a lower load. So we can recommend, let's say, you can use it at lower load and continue using it until you have a replacement. For long-term issues, we can plan for a next inspection. So you want to be able to trend, let's say 2 months from now or 6 months from now, is this degradation getting worse, or is it around stable rate? And then what is your next plan? You need to do measurements during this kind of inspection also. Partial discharge, for example, can give a good identification. Thermal measurements, infrared. Sometimes we do repairs also for long term, and then revision, whether we need to replace or do other things to the system. The idea of condition assessment lies in the part of the yellow box here, yellow square. So visual inspection, non-destructive testing, and performance testing. So this is where condition assessment plays on, but it feeds data into predictive maintenance and risk-based maintenance. We'll touch about that on those 2 points later on. But you just need to know that this information is feeding to the next steps. So assessing condition, equipment condition, there are various importance. again, there are many stakeholders involved. So if you go to the management side, asset management side, they will want to know, do we have to replace this asset? If we have to replace, what can solve this problem? Can we prolong it? Risk management, they always look at whether or not the impact of a failure is going to happen and what is the result of the failure. Can we manage this or should we replace it? Cost optimization, performance, of course. Cost optimization, we don't want to replace immediately, for example, but we will replace it soon. As long as can run safely, we want to run it to the lifetime. So those kind of things. Compliance and regulations, DOSH, Department of Safety and Health, for example, they may require a condition assessment before restarting a power plant. When you have a major overhaul, before restarting of a power plant, it is in Malaysia at least, it's a requirement that you do a condition assessment. And so power plant owners need to run this kind of assessment before they are able to get a permit to restart their plants. Performance monitoring, degradation, for example, in a solar plant, what do we do? Let's say you have a solar panel which degrades of about 1 to 2% every year, but somehow you have a degradation that is more than that, and you have degradation. If it's only a few watts, it's no problem. But if you have 100 megawatt plant and you have a 2% loss, it translates to quite a lot of money. Insurance also is interesting. My experience in Europe, where you have wind farms, inter-array cables, where you have cables between the wind turbines and the submarine cables. Right now, insurers are having a big debate about how much more can they insure it for, what is the situation, because a lot of these cables are experiencing quite fast breakdowns, 5 years, 3 years, 2 years. And now for new projects, people are getting quite difficulty in trying to get insurance for these submarine cables because of the trend that is developing. Of course, it's a learning curve. Later on, when we know more, we will be able to overcome the issues related to the failures. But these are things that they want to maybe be able to do a condition assessment of a wind park to be able to next get an insurer to insure these assets. Data-driven decision making is something that we will touch here. Stakeholder confidence. Yeah, of course, you have investors, you have managers, managements, people, and those people want to be able to know that they can have sleep. They will not have sleepless nights when failures happen. They don't want another failure to happen very soon. At least take some time, give a breather, learn about it, and maybe be able to solve the problem. So if you have a condition assessment, you can address this. Sustainability, yeah, you don't want things to leak into the ocean, for example. You don't want transformers to burn and release a lot of toxic fumes. So before such occurrences happen, you are able to give um, some form of comfort for people who are into sustainability. Here, what we notice is that data-driven decision making. Data-driven decision making is what fits the is what fits everything else in this graph, in this chart. So you need to make some form of decision in all these parts. But the main part which gives us the power is data-driven decision making. So this is also a bit on health assessment. So this is an example of an asset health index. So what to do when you do some form of maintenance or testing. If you detect defects, if you don't detect defects, what to do next. It's a guide only. It depends a lot on failure probability and consequence. This guideline normally is made based on a set of knowledge rules. After looking at many years of data, people like consultancy companies, they are able to give a form of classification. There are some papers already out which are looking at this as well. So for example here, when we look at no defect, that means you don't need to do any action, you can continue running the asset. If you look at possible defect or early stage defect, you need to do also later tests, further diagnosis, whether or not the set of tests that we give, we have subjected the equipment to is sufficient, or do you need to do more tests? This is also quite important. When you look at the defect, probable, so it jumps from possible to probable. Then you need to really look at further diagnosis, and then you need to look also at the decision repair at next occasion. If you know that it is a defective part, you don't want to run it for many more years, but you want to repair at least at the next possible time when you have a shutdown, for example. When you already are sure that there is a defect, example that I can give is a partial discharge measurement, and you know that there is a partial discharge development in your power cables. It's maybe a bit difficult to repair cables with partial discharge, but you need to replace them. So you need to plan a replacement. Power cables can run for many kilometers. So which parts of the cable do you replace, or do you replace everything? This can give you a bit of insight. So in terms of decision making, it's not so easy to replace an entire circuit. I'm sure some of you have already experienced this before. So a bit of guideline helps in your decision making. So example of a certainty of the defect or critical, when certain partial discharge readings go beyond the range of safe operation, you already know that it's going to fail. And rather than, of course, you don't know if it's going to fail in 5 days or 5 weeks or maybe 5 months, but you need to already plan for an immediate repair. Because, for example, again, failure probability and consequence, if you can bear the consequence, you can delay or defer it. But if it's something that you cannot bear, the result of this failure cannot be taken up by your organization, then you need to plan for an immediate repair. So these are things that are related to the table just now. So when you do an asset life management, you want to look at regulatory framework. Maybe you have a reference period of how long you want to run this asset for. Suddenly you have a lot of failures happening, failure within critical time. You don't want to continue purchasing, for example, more assets until you know more. Maybe you also don't want more people to operate it in person. You want to have some form of barrier, dead operation only, for example. So this can give you some form of safety net as well. We are about half an hour now. If you have any questions, just please let me know. The next topic is fundamentals of condition and remaining life assessment. So we touched about condition early on. We also touched about a bit on the remaining life part. Now we come into the condition and remaining life assessment. So you want to be able to look at the current situation, what is the condition of the asset, and you want to have a bit of insight about how long you can run it, the remaining life part of it. So there are many names that are given to this. There are people who call it condition assessment and remaining life. Some people call it remaining life assessment. The former organization where I used to work, they call it condition and remaining life assessment. So I think it's a very nice name because it gives you a complete description of the situation, the condition, and how long you are able to run it. So the equipment lifetime, we can look at it as the past, the present, and the future. What we can look in terms of condition and remaining life assessment is look at the past as well, not only at the data that is present today, tests that you have done today, monitoring that you have done today, but you can also look at the past. You can look at the age of the data of the equipment, the loading, of course, operation, whether you switch it on and off every day, or does it run frequently only at base load. Maintenance data, you can look at whether or not certain parameters are progressing fast over the years, and failure data. So failure data is something that I like to stress here, because my focus is in failure investigations, and failure investigations is a powerful tool to understand also the current situation. So looking at the equipments that have failed, you can gather some insight into what is the situation of the other assets that you have, whether or not sister units that are installed in your system are going to also possibly have this similar problem. Maybe they are exposed to the same operating conditions, maybe they are also same age or batch. Then you can expect that possible developments are also happening in other units. Condition assessment, like we already spoke about earlier on, and remaining life assessment, loading guide. So after you do a remaining life assessment, you are able to look at loading guide calculations, whether or not this remaining life can be improved by reduction of load, reduced load. You can do also fulcral analysis. This is for transformer oil. You can look at the current degradation of paper and oil in the transformer by doing this test. Trend analysis, and look at also O&M practices. Internally is good, but it's also good to look at what the other customers, the other parties, or the other O&M companies are doing. Maybe there's something new learning from their practices within the industry that we can also adopt for your asset. So the steps, so for fixed asset data, we can do inspection. Operational data, you can do online measurement. This is something that is becoming more and more prevalent these days. Online measurement, maintenance data, offline. Of course, when you shut down, then you do some form of maintenance or testing. Diagnostic data, so you open up or you go into a transformer and look at what is happening inside. Events, then you look at the test. The step-by-step approach, it's actually fine-tuning or funneling you into the right direction. So you start with a very wide area, analysis of relevant historical data. It may give you some direction of where this is heading. Then you do the step 2, which is visual inspection. You can interview and condition scan. So you narrow down your target now. With online and offline diagnostic, you become a bit more sharp. And the best is when you start doing internal inspections, tearing down or opening up equipment which have failed or aged, and then you can look at the mechanism better. So it's tapering down to a better range of accuracy, I would say. But you need to do this step by step so that you do not get deviated with many data which are not relevant to the situation, and it is getting somewhere. It gives you hope that you are getting somewhere. So conditions can sit here. So when we look at the situation, fixed asset data, you do the inspection, we do the operational data analysis, and look at trends that are developing. So this is a method, maybe not so much for today, but these are some methods for measuring condition of an asset. So it's a very deep subject, but what I'm sharing with you is just a list of tests that can be done for measuring the condition of an asset, for determining the condition of an asset. Yeah, so if you do for a circuit breaker, for example, your contact position, they call it a white position, contact velocity, vibrational analysis, trip coil. So these are all part of the mechanical part of the circuit breaker. It gives you an indication of whether or not a load can be broken fast enough. whether or not it is reliably and repeatably doing the work. Then you look at the primary context inside of the vacuum interrupter. What's the contact resistance? Is it becoming worse over time, or has it remained static over the years? Overall, dielectric test, PD, vacuum leak test, oil analysis, SF6 analysis. So these are a list of tests. We can touch on this specifically when, let's say, if you are interested later on. But just know that there are some tests that we can carry out for condition assessment. So next one is maintenance. So when we do condition assessment, we also look at maintenance. Maintenance, yeah, is an activity. It's a list of activity that we carry out to keep an equipment functional for functional. So you want to do maintenance to make it functional, to have it operate as how you expect it to operate. So some aspects that we look at are the quality, reliability, availability, and safety. Cost, whether or not doing maintenance and replacement work is expensive, because if it's too expensive, maybe just replacing the part is cheaper. Not the part, I mean replacing the whole component is cheaper. So over time, spare parts can get quite expensive, and you want to decide whether or not you want to have further replacement. But if it's not financially viable, sometimes it's good to have a complete replacement. Risk, again, probability and the consequence. So you always have a function of these three. What is a balance, good balance of these three? If you look at the graph on the right, so this is a nice graph for the effect of doing maintenance. So over time, you want to look at what is the degradation or condition. I will give you an example of a solar panel, for example. So a solar panel, when we have it degrading by about 1 to 2% in a year, is based on the construction of the solar panel and chemistry. But there are other factors that also affect the performance of a solar panel. Things like soiling, dust collection over a panel can quite significantly affect the performance. And so when it runs for a certain period of time, as more and more dust is collected over the panel, and let's say they do a cleaning, a maintenance is done, you have an improvement in performance, a small but worthy improvement in performance. So let's say if you do not do the maintenance work, it continues to degrade. You also have more heat generated because it's less, the performance is less. So your degradation starts to go on and on. And if you don't do a maintenance, you have a remaining life of, let's say, here. Okay, right? But if you do a maintenance program, and you are able to extend the remaining life to a certain period of time, sometimes quite significantly. Just a small oil change in a car, for example, is important to extend the lifetime. And if you don't do that, your car might just break down quite soon. But if you do periodic maintenance over time, you improve the situation, you improve the performance, but also you improve the lifetime. You extend the lifetime. This is what the graph is trying to show you. Some maintenance concept, corrective maintenance. I think these are terms that are quite frequently used also in your industry. Corrective maintenance is when you do the repair after a failure. So this is mainly what was done 100 years ago. Those were the things those were the days, I would say. So when a failure happened, you replace it. But otherwise, you run to failure. This is the concept of previous years, about 100 years ago. Today, it is still applicable. It is applicable for things that are low impact, local or small scale, and no risk to life. For example, if you have a solar panel on a rooftop solar panel, if you want to have it replaced periodically, maybe after really a number of years that you replace it, because of the impact which is small, you do not lose too much revenue, but at the same time, it's not worth replacing. So you want to do it when it fails. The same equipment, if you go into a large scale solar plant, for example, and the losses are quite significant, 1 to 2 to 5%, for example, and the result is that you have a significant loss in revenue, then the impact becomes big or medium. So you want to start to prioritize it. So there are the same type of equipments, but different application. It can result in different type of impacts as well. Just for you to know, preventive maintenance is also something of yesteryear, which I consider yesteryear. It's a time dependent. For example, your car, they have based on time, right? Every 6 months or 10,000 kilometers, for example. So these are based on time, and also usage. So time based and also cumulative usage. How many kilometers you have traveled. It can also be event based. If you look at it, sometimes you have events that you think, okay, this is a good time for you to change the oil because let's say you have some leak in the gaskets, so you want to replace the gasket, you do the replacement. It gives you a bit of an easy planning approach, so you don't have to think about this too much. You just use the 6 month or 10,000 kilometer as your guideline. So every time you look at it, you just say, okay, in the 6 month, I will replace it. Or if I reach at 10,000 kilometers, I will do it. But there is a part which is also known, again, for cars and other application, again, also for power system equipment. Your chance of failure increases with time or usage. So if you have an asset which is 20 years old and you continue doing this kind of maintenance, you increase the chance of failure. So you don't want to reach a failure and then think about the rest of the problems that comes with the failure. So time dependent type of an approach may be a bit less powerful compared to the current approach. So condition based is something that is quite trending after the years of 2000. We see facilities optimizing, efficiency improving. You also have effectiveness of every practice when you do the maintenance improve. So you don't want to have a faulty part and then you do the replacement. But if it's aging well enough, you think it's good time to do it, you can already make a decision. So there is also again a precondition. You need to have a gradual or predictive degradation. So when it happens with a degradation mode, you have the graph of or curve of trend that is progressing. It is possible, and you need also data. So because if without data, you cannot do condition maintenance, availability of measurable indicators and knowledge rules. So you with CBM, there is also one part which is nice. It allows the asset owner to defer maintenance. Sometimes you think that, okay, the asset is doing well, but we don't need to do it so soon because we have not used it to the maximum loading, for example. So you can defer based on the condition, you can defer maintenance to another time. Saves you money, saves you time. Topic 7, replacement decision making. When to replace is always a chicken and egg question. I think everyone has a question like this in the organization. When is a good time to replace? You always consider performance. If it's really poorly performing, you want to replace. You also consider cost. If renewing, for example, in the graph here, the renewal cost is about twice of maintenance cost. You want to continue to do maintenance, not twice. Here, I think it's about 3 times the routine maintenance cost. If let's say you replace it and it's 3 times the cost of routine maintenance, but by doing routine maintenance, you have still a good remaining life. You want to maintain doing routine maintenance. And then comes the risk. So like we already know, as the age increases, the failure rate also increases, and you want to do an assessment of the risk, how much is it, how far it's going to impact your organization. So it's a chicken and egg question. This, you have 3 chicken and eggs to balance, and yeah, it's not an easy task. Where condition assessment and remaining life assessment, condition and remaining life assessment comes in handy is by giving you the data that you need. So in short, data-driven decision making is not based on a person who makes the decision, but it's based on a set of data, a pattern that is developing, inference or data that you look at other people's operation or certain parameters, insights. These are things that are giving you an idea of the actual condition. So data-driven decision making is a nice way to approach this chicken and egg problem. Previously, I like to also use this terminology, this example. Previously, when we have opinion of one person versus opinion of another person, the highest paid opinion wins. So the boss always wins. In recent years, opinion versus data, and data always win. But now we look at the quality of data as well. So when you have data versus data, the best data wins. So the more data that you have doesn't really mean that you have the best data. In terms of AI, for example, rubbish in, rubbish out. So sometimes if you feed rubbish data into AI, you get poor results, not accurate results. But we want to have good data, and condition assessment is a good way to have good data. So you have sound judgment, and you can deliver expected results. So we are approaching maybe a bit towards the end of our presentation today. Topic 8, future trends. There are many future trends that are developing, but I think I will only touch on a few that can be relatable to most people today. In many areas, there are a lot of research being done to help to give data that is needed for condition assessment. Yeah, it's developing and it's getting more exciting. Trends in maintenance, we already know that before it was corrective. Now, recently it's been periodic. Now it's becoming condition, and later on it will also come into this base optimized mix. There are evolution in diagnostic monitoring technology, introduction of intelligence, AI, computerized maintenance as well. So you have programs that run the management of maintenance, trend analysis, predictive techniques. We spoke about health indexing early on. Future trends. I think it's already 2024. We should not be saying it's future trends, but there are many new sensors as well being deployed these days. So sensors that you can already install in equipment, giving you live results by IoT, Internet of Things. And you can really plug and play which parts of the equipment do you want to monitor. It gives you a lot of power, sensors and IoT. Another nice example is the automation of drones using automation of transmission line monitoring using drones. So what they do is they preset a program for drones to travel, let's say 20 kilometers a day. You don't even have a pilot. The drone does its own flying. They set the map and how far it will go, which towers for it to inspect. It goes and does the job, it comes back, recharges by itself, and goes out and does the same thing continuously. So you don't even need a person to be behind a remote control to do this anymore. So these are nice technologies that are developing. Automation using programs is good because it gives certain aspect of flexibility where you want it to be done continuously and repeatedly. You don't really need a person to be there. It gives the person uh, a better flexibility to do other more important things. Integration of AI, artificial intelligence, machine learning, and deep learning. So we go as we go forward, AI is going to be a bit on the yesterday's story. So we have more on the machine learning and deep learning. It refines more, furthermore, the decision making part of data-driven decision making. So as we go, we learn, and the machine learning takes up a lot of data. The results become more refined. You get quite well, quite good at it, at making decisions. So we are now at the conclusion part of our presentation today. Um, I would say that we discussed quite a lot of topics for this 1 hour presentation. But what's nice is that you can take home something. You can take home some value, some points from our discussion. And later on, if you are interested, you can approach Erudite or any other training providers to look at the specific questions that you have related to your problem in your organization. So I'm sharing with you the first one, what we look at early on. So lifetime estimation. Lifetime estimation is based on design, laboratory testing, simulation, but it's not always 100% shot in real life. So non-ideal conditions exist, and when they happen, you can extend or you can reduce the remaining life of an asset. The next one is health indexing. So health indexing is a guideline. So what for you to do next for each current condition? This is arrived at based on knowledge rules, which has been gathered over time, and so it gives you some form of guidance. We spoke about the effect of maintenance and how it can prolong your lifetime of the asset. It can also defer or delay maintenance based on condition-based assessment. We spoke about the chicken and egg situation. When data speaks, we always know that everyone has to listen. When data speaks, everyone listen. So deep data-driven decision making, it gives you an ability to make sound judgment, and it gives you also the ability to deliver expected results. I'm at the end of my presentation. So if anyone has questions, maybe.
Okay, all right. So thank you, Sir Rafi, for that insightful presentation. So yeah, the floor is open for any questions this far. So before I flash on screen some of the questions I've collected, is there anyone who would like to grab the mic or raise a hand? Okay, none so far. So yep, I actually gathered some questions. Hold on. Okay, so here's sir some chat questions I've got. First is, at which stages do we carry out a condition manage assessment? Is it necessary to assess an asset's condition during commissioning?
Okay. We did touch about the topic of which stages to carry out an condition assessment just now. So we covered the cradle to grave chart. And so when an asset is put into service, um, it's a good time to start, because I would say that although you have not experienced actual aging of the asset yet, because you are starting at 0 years of operation, but it gives you a good baseline data. Where is the asset at the birth or the installation time? So if you do a condition as assessment of an asset during commissioning, you have the baseline data to start off, and then over time you have already developed a trend. So even in the first year, you are able to look behind what's happening from previous to the current situation, and I think it gives you some power for analysis.
Right. So, any follow-up questions on that? Not, I can probably ask the second one. Okay, no. So, our company invests in buying over existing solar plants from other asset owners. How can condition assessment help in our decision process?
Okay,
The second
okay.
question.
This is a nice question. Buying over existing solar plants is a very expensive affair, and trading plants like this has become the trend also in Malaysia. Previously, it was happening around the world, but now I'm also looking and seeing that this is happening locally as well. So people who build solar plants, they are called EPCCs, engineering procurement companies, and they build, they also install, and they run for a certain period of time. Uh, and they run it for, let's say, half a year or so before handing over to the owners. So this period when they run it and later on hand it over to the owner is when the warranty period of a solar plant starts. When people also look at the how is everything performing, how well is it performing, will they be making profit from selling power to the grid. But sometimes there are also issues with financials, and people, some companies, they are no longer interested in running a solar plant, and they look for customers to buy up from them. So when they start to look for people who will buy a solar plant, they are also selling the PPA, power purchase agreement, with the government. So it's coming hand in hand. You have an asset, you also have an agreement with the government to sell power to the grid. Uh, and the new companies that want to buy these solar plants over, they will want to also assess the situation, because there has been a time lapse. There has been also some form of operation and degradation. They want to assess whether or not they are making a good buy. And condition assessment helps in this situation. Things like an audit, energy audit, system audit, installation audit, it helps. Condition of each assets also help. So when you have all this information in front of you, you are able to predict how much you will make over the next few years of operation by selling electricity. So this condition assessment is a useful tool actually when you want to have handover of assets to different parties.
Okay. So, thank you, sir. Last question, I think. We are a manufacturing facility and we have experienced cable failures in the circuit at our plant. How do we assess the overall condition and remaining life?
Okay, this is also nice, an experience that I had before I started my small company. There was a plant somewhere in the Middle East which had issues with the circuit, the cables. It's a chemical plant, so there is possibility of chemical contamination in the ground, and this could have resulted in cable failures. But they are not sure. They are not sure of the condition in the ground. They assume that it could be from the environment itself. The ground itself has some form of issues, uh, but there is a possibility of some other factors affecting the cables in this installation. So what we offered them as an organization was to do a condition and remaining life assessment, but also to pair it together with failure investigations. So they do some form of test. which we already listed this just now, and we analyzed these data. Some of the cables which failed, they stored. And so these were valuable information providers for us. We open up these cables, we do chemical tests, we do electrical tests, we do specification or dimensional checks to make sure that the cables are as specified, designed, and we are able to pinpoint a bit further what is the root cause of the failure. And from this, we can also pinpoint if the other sides of the cables or the other length of the cables have a likelihood of similar degradation. So it gives us an assurance that, let's say, if you have the similar soil condition, you would expect an entire length of cable to be having the same problem. So this plant, they cannot afford to have breakdowns. This, let's put it as that. They cannot afford to have breakdowns. It Once you do this kind of condition assessment paired with a failure investigation, you are more certain that you are doing the right decision by replacing the entire circuit. So you doing a condition assessment and deciding on replacing a circuit. Everyone knows if you have 2 kilometers or 1 kilometer of circuit, it costs a lot of money to do a replacement work. It costs a lot of time to do this as well, but they can balance it out whether or not they want to do this or they want to face a risk of failure in the future. So this gives some power to the decision making. Yes. Wins, I see a hand up.
Mr. Vince?
Yes, thank you, Rafiq. And first off, thank you very much for facilitating this webinar and very informative webinar for us, as well as to our attendees. I do have a question, Rafiq, in reference to the trend that I am seeing among local utility companies where they are now incorporating battery energy storage systems. So one of the questions that I would like to ask you is, what are the condition assessments for these types of technologies? And also, what are your suggestions on how we can manage these kinds of new assets that they have incorporated in our organizations?
Okay. Yeah, that's a nice, interesting topic. Which thank you. Battery storage, it gives a lot of flexibility to the grid. So you don't have to generate with more renewable energy connected to the grid. You know that solar, for example, or wind doesn't generate electricity 24 hours. So you have moments of good generation and you have moments of very low generation or close to zero generation. So you don't want to have an imbalance between day and night. What we can have is a battery storage where you can store excess energy and later on sell it to the grid. That's one application. There are many more applications related to battery storage and selling to the grid. But what happens with battery storage is that it passes through different parts of the grid. It passes through different parts of AC components. So you need to pair AC to DC. Battery is DC and you have AC. The part which converts AC to DC is a converter, essentially as an inverter, and that also comes with different parameters to monitor. So if I focus only on the battery part, the main problem with battery is thermal runaway when batteries start to heat up from charging and discharging and development of chemical imbalances. So they start to heat up and you have problems like a fire developing. Batteries, when they catch fire, they don't stop. So lithium ion is quite a continuous burning issue. So the risk is high. In this situation, I would call the risk high. Uh, how do you monitor it? The question that you asked, the important part. So existingly in battery storage, because they are quite recent technology, manufacturers have already installed things like battery management system, energy management system, which monitors it automatically. And when the risk is too high, it isolates certain parts of the battery. So it goes to zero volt or zero current. Existingly, there's already a situation where it monitors itself. But this data is valuable for your long-term prediction, how long it's going to last. So you have charging and discharging, which affects also the um, expected remaining life of batteries. So every time you have a discharge and charging, you actually impact a battery storage system. They say that it is about 8.2 to 12 years of expectancy for typical grid connected battery storage. When you have more operation, charging and discharging, you reduce this lifespan. And so with data that is present already in the monitoring system, you can actually look at spare part management. You can look at when the battery technology has become obsolete, what kind of options do you have in the future to replace the existing infrastructure? So things like that. Also the plug and play nature, because batteries are modular, you can add on capacity and you can become a bigger service provider for battery storage. So things like that give a bit more power.
Thank you so much, Rafiq.
Yeah.
Right. So it's 4:20. So thank you for those wonderful questions. And I would like to take this moment to or opportunity to end the question and answer portion and thank our wonderful speaker for being with us here today. This 1 hour and a half webinar of introduction to condition and remaining life assessments of power utility assets. All right. So Sir Vince, since you're still here, would it be all right if we can have you present our appreciation to our speaker for today?
Of course, my pleasure.
Right. Oops. There.
Thank you very much, Rafiq. It's my honor to um, share with you this certificate of appreciation. And this is awarded to Mr. Nurul Rafiq Namas Khan in your recognition of your outstanding contribution as a speaker in the Introduction to Condition Remaining Life Assessment of Power Utility Assets webinar. Your dedication, expertise, and commitment to the task at hand were instrumental in ensuring the success of the event. Given this 13th day of March 2024, signed by myself, and once again, maraming salamat sa iyo, Rafiq.
Yeah.
Datang salamat. I don't know if that's how you say it in Malay.
Yeah. It's a terima kasih, I think. Yeah.
Terima kasih. That's
Yeah.
right. So
Yeah.
thank you so much. And we will send over a copy of this to you.
Yeah.
And we hope to see you on our upcoming conference as well as to our plans for conducting a more comprehensive um, training on this topic and other topics that Volta Forensics. So can I invite everyone to give Rafiq a virtual round of applause? Thank you so much, Rafiq.
Yeah, thank you very much also everyone for taking time to attend. Um, just to my last words, maybe if you can also keep in touch with me on LinkedIn, it would be nice. Of
Yes,
course, if you have questions related to power failures, I'm more than happy to help you. Also, if you need training advice, I think you can also come to Erudite because we are, of course, doing this jointly. If you need trainings, those are things that I also do. Thank you.
Definitely,
definitely.
if you have any other inquiries regarding Volta Forensic and Sir Rafiq, you could always message us or email us at info@erudite.com.ph and we are more than happy to assist you. Okay, so yeah, thank you, Sir Rafiq, and I would also like to thank each and every one of you to in attending, in sharing this time with us and this afternoon with us. I've shared over. Yes, but we can give you copies of these slides. We would be sharing them. We would be emailing them to you. If you would also notice, I have shared a Google form on the chat section. Kindly answer the post evaluation surveys so we would know how this topic impacted you and we would know from there. Okay, and then afterwards you would be sending the recap of this webinar as well as the materials from Sir Rafiq. All right, so I do have a few more announcements before we end today's webinar. So first of all, we have a conference coming in on July 3 to 5 here in Manila, Philippines, and the early bird promo for it, APM LeadCon 2024 Sustainable Futures, is coming to an end this March 26. So make sure to grab this opportunity and register to save your slots. You can find out more on the event website and their social media pages, APM Lead Conference and Exhibition. We are excited to see you this July here in Manila. And then on April, you don't have to say for that. On April 12th, that is a Friday, we invite you to another webinar with Eurison about unlocking the power of reliability as a service for control valves with speaker Mr. Jules Udmans. If you are interested, wait for further updates on registration coming soon on our social media platforms. So make sure that you are connected with us on LinkedIn, Facebook, and YouTube. Right. So, okay, let me just.
Do we have a group photo for those who are still around?
Yeah, can we do that? Can we open
I'm not
our?
available for group photo because I don't have any. I'm sorry.
Yeah,
I
it's
have
okay.
no. My background is not.
No, it's okay,
It's
sir.
okay.
Yeah, yep. Just for those who can open their cameras
Okay.
and join
Okay.
us.
Thank you.
Hold on. Let me put it on gallery view. All right. So thank you for allowing us to to see each other. So I would be asking help from some of my colleagues, Miss MJ and Sir Lily, to snap photos. All right. So everyone smile. I missed someone. Okay, so there we go. So once again, thank you everyone for coming in, and we hope to see you once again on our next events. Thank you everyone. Thank you, sirs.
Thank
Thank
you,
you, everyone.
everyone. Thank you, Rafik,
Thank you, ma'am.
Yes, my pleasure.
and God
Thank you,
bless and
Rafik.
keep safe.
Yeah. Take care, everyone.
Bye for
Rafik, if
now.
it's okay, stay put for 5 minutes.
Yeah, yeah, of course.
Okay.